I'm Steve Anderson, Associate Publisher and Editor-in-Chief of Laser Focus World. And we are pleased to partner with Clio again this year to support the Innovation Awards program. The program was established to honor exhibitors who have demonstrated outstanding leadership and made significant contributions in advancing the field of optics and photonics. Each year, we recognize some of the most timely, groundbreaking products in the field of laser science. Entries are judged on criteria vital to product success, including impact, functionality, life expectancy, impact on the optics industry, innovation, and patents or trademarks. The grand prize winner of the 2011 Clio Laser Focus World Innovation Award is Applied Research in Photonics Incorporated, which was given the award for the development of a highly sensitive, low-power terahertz scanning reflectometer that's capable of directly measuring both the concentration gradient and kinetics of permeation of an ingredient across the thickness of a substrate in real time and in a non-invasive way. Please welcome Anis Rahman, Applied Research in Photonics CEO and CTO, and Anup Rahman, who's Senior Engineer, who will accept the award.
Hello, I am pleased to announce that the winner of this year's 2011 Clio Laser Focus World Innovation Awards is Applied Research in Photonics. And they are the winners this year for a very unique terahertz scanning reflectometer system. And I am here with Anis Rahman. Anis is CEO and CTO of Applied Research in Photonics. And Anis is going to tell us about the instrument and what its capabilities are.
Thank you very much for this opportunity to talk to you, Gabe, and thank you for arranging this. So, the product that we built is called Terahertz Scanning Reflectometer. So, it has two capabilities. It can scan and it can measure the reflectance. And the application of that is primarily in transdermal research, personal care products, and transdermal drug delivery area. But it can be used with any other substrates. So we have a terahertz source in this box, which is a continuous wave terahertz source. And that terahertz source then arranged in a way that it will be reflected off of a substrate and back into the detection system. And the substrate has an arrangement that can be, the distance can be lowered or higher from its focal point. So the idea is that originally if the substrate is at the focal point, and then let's say you apply some ingredient on that substrate, which could be skin, which could be some other biological tissue, or any other substrate that terahertz can penetrate through, so it will not work on metal. Other than metal, any non-metallic substrate, it will work. Believe it or not, there is not an instrument that will non-invasively measure the kinetics and measure the concentration gradient all in one machine and in such a simple manner. So that's one of the innovation in here, that terahertz is being applied in all different kind of ways, in imaging, in spectrometry, like we have another spectrometer here. But we thought that this is a much needed measurement system that is not present in the marketplace. So we have been working on this about 2 years now. And we should give credit to our collaborators. We collaborate with Professor Bo Mishniak's group at Rutgers University. They have been providing us with stratum corneum samples, skin samples, and they also employed their graduate students to work on not on the machine, but on the science related to it, doing measurements and interpreting the data and so on and so forth. But I think the key is that we are able to measure not only the kinetics but also the distribution of the ingredient across the skin or other tissue in a non-destructive way, in a non-invasive way. So this will be a diagnostic tool in hospitals or doctor's office. This will be a research tool in the laboratories, universities, and being it the first generation, we hope that there will be more improvement of this system to get into another, all different kind of areas. For example, the melanoma or skin cancer detection, or tooth, looking inside the tooth, breast cancer. The early detection is so important in those areas, and also in connection with the spectrometer, we are doing work to understand the molecular origin of the cancer. And this is important because the cancer is not a simple process. From the cellular point of view, a healthy cell, when healthy cell goes to cancerous cell, it takes a long time. It's a long journey. And doctor at the current rate in present technology can detect that only when the cancer is already full blown. So, of the 4 phases, it has to be at least first phase of the cancer for one to be detected. But it's initiated a long time ago. So if doctors could trace that, okay, this gene is now doing this kind of behavior and it has the possibility of turning into cancer, then they could do something about it. And this machine and along with this spectrometer, we are doing that kind of work to understand the molecular origin of healthy cell turning into cancerous cell. So those are the areas. It's not ready yet, but we hope to be in there, hopefully in our lifetime. So this is giving us the baseline. And now what we want to do is look at the kinetics. So this is just deionized water. It's DI water, nothing in here. And what I'm going to do is take a small drop and put it on this substrate to let it permeate through. So okay, so I have some water here and I will put a drop of water on, and as you can see, as I put the water and the water penetrates through the paper, the reflectance is directly proportional to that. So, and eventually when the penetration is done, then it will saturate, it will go to a straight line. This is the time, so as you can see, this axis is the time. So this is the measure of the time that it is taking for that water, small drop of water, to go through that paper to the other end. I put methanol, and let's do another demo of that. Methanol goes much faster, and you'll see almost like that behavior. So it's going to go to saturation. So let's stop this one now. Eventually it will go saturation, but let's take this away and put another paper for methanol. So methanol goes much faster than water, and we can measure that. In fact, we have done measurement with other liquids, methanol or ethanol or oil or rub or something like that. Everything has their own characteristic kinetics, and so this is a way that then a researcher or doctors will know where is going what, how long is it taking, and then they can come up with a better diagnosis. So that is so simple that we made, and user-friendly. All you have to do is run a program, put the stuff in there, run a program, and then that's it. So what we want to eventually do is make an arrangement so that, let's say I'm putting something here and I can put my arm over there and do the measurement. In fact, a lot of dermatologists has asked us if we can do it, and that's the next step, so for us to be able to do that.